Hi everybody, and thanks for listening to my talk. My name is Alyosha Oshep, and I'm a postdoc at Technical University of Munich, where I'm working with Laura Lealdashe. I'm very glad I can talk about our recent research today here on a workshop on perception and control for autonomous navigation in crowded and dynamic environments. Today I'm going to focus on perception. So let me first quickly motivate research topics that I'm going to talk about today. So what we want to do here is to enable mobile robots, such as those that you see here on top, to navigate and move around the world. And for that, robots of course need to be able to detect and track objects. In addition to understanding where objects are and how their trajectories evolve over time, they also will need to be able to understand the semantics of the statics in structures. So for example, to plan our trajectory, we need to know where the drivable area is. So first, I'm going to talk about our contributions towards such a holistic video scene understanding that encompasses object detection, segmentation, tracking, and semantic segmentation. Then I will move on to the next great challenge that we need to solve here, and this is the challenge of tracking arbitrary objects. So for example, here in this visualization I'm showing here, we trained our detectors using labels for car and pedestrian classes, and we are able here to detect and track pedestrian classes, object classes reliably. But what about this child stroller over here? So we didn't train a detector for a child stroller class, and we are essentially blind to that object. And this is something that can lead to disastrous consequences. And there were such cases observed before, where a Tesla car that was on autopilot didn't recognize fire truck as an object and just accelerated and crashed straight into that fire truck. So of course you might be thinking now that we can now just go outside, record and label more data and train detectors for child strollers and fire trucks, but I would argue that it's not quite that simple because of this long-tailed and unbounded object class distribution. Because this distribution is unbounded, it means that essentially we will always see novel object classes during the deployment that we didn't see during the training phase. And for many objects that we will make it to our training set, we might observe only very few examples of that particular object class. And that's why I would argue that we will not be able to just simply collect enough training data to train object detectors for every possible object class. So in the first part of this talk, I'm going to focus on holistic and dynamics understanding. So here I'm going to talk about tracking every pixel of the video or every 3D point coming from a stream of LiDAR sensory data. Then in the second part, I'm going to move on the topic of tracking objects in the open world, in which the set of object classes that has to be tracked is unbounded. So here I'm first very excited to present our recent work called 4D Panoptic LiDAR Segmentation. And this is a joint work between our research group at the Technical University of Munich and a group of serial technicians at the University of Bonn. And we also presented this work recently at CVPR. So here I'm going to talk about LiDAR-based scene understanding. So nowadays many robots come equipped with a LiDAR sensor. And when it comes to LiDAR-based scene understanding, several methods tackle semantic segmentation of LiDAR point clouds. So this is the task of assigning semantic meaning to every 3D LiDAR point. Then recent developments have actually been moving towards a holistic scene understanding that jointly tackle object instance segmentation and semantic segmentation. Overall, the task that encompasses both is called Panoptix Segmentation. So previous work has been focusing on the interpretation of individual scans. Orthogonally, 3D multi-object tracking methods would usually first train 3D object detectors for specific object classes, and then the inference time we detect objects independently in LiDAR scans, and we associate these object detections over time to get such 3D multi-object tracking results. So here in this work, we actually propose a task called 4D Panoptic Segmentation that unifies all these perception tasks. So for this task, we need to assign semantic meaning to every 3D point in a sequence and a unique object instance ID in both space and time. So in terms of tracking, I would first like to reiterate that most existing methods follow tracking by detection paradigm. And here the idea is that we train first object detector, and then in each LiDAR scan individually we would apply our 3D object detector, obtain object detections, and then by some means we would associate these object detections over time to get such results, so such object tracks. And here we decided to go for something quite different. So we were inspired by perceptual grouping theory that essentially says that points that look similar are nearby in space-time and have a good continuation likely belong to the same object instance. So therefore we post here tracking as grouping of 4D spatiotemporal volumes. I would here also like to acknowledge that this idea of tracking as clustering we first introduced in the context of video object segmentation in a paper that we published at ECCV last year, and I will also briefly cover this in the next slides. First, the overall idea here is guided by the question whether we can learn 3D point embeddings for a point cloud sequence, such as the one that you can see here on the left, such that points that correspond to the same object, here for example denoted in green, are mapped nearby in the embedding space. And the key insight here is that object instances can be modeled as Gaussians in the short spatiotemporal volumes. So if you model them as Gaussians, what you want to do is we want to evaluate probability that certain pixel, let's call this pixel within the pixel I, belongs to certain object instance J. And to evaluate probability of pixel belonging to this instance, what we need is embedding vector for our query point or pixel, and we need embedding vector that represents our object instance J. And we also need a variance vector for our object instance J. And this will be exactly the parameters that we need to learn in order to evaluate this probability for every pixel or point in the volume of belonging to certain particular object instance. I will elaborate this more in the next slides. So first of all, let me explain this on the example of video object segmentation. So here we want to segment and track objects, and what we do here is we would take a short video clip, we would stack images together, and we would pass such a spatiotemporal volume that we obtain by stacking images through our encoder-decoder based architecture. And on top of the decoder we have three network heads. So the first network head will give us embedding vectors for every point in the volume. Second one will give us variance vectors for every point in the volume, and the third one is kind of point-based object detector, point-based temporal object detector. So this will give us for each point in the volume probability that this point corresponds to a center of a particular object instance. And then once we trained our network to produce all these outputs, we can do the following. So looking at this short video clip that you can see here on the left, we have two instances. One is the rider and second is the horse. Then we'll first look at object heat map, and we will take out the value that we will essentially take out the argmax, so the point that most likely represents some object instance center. We will look up at the coordinates at this maxima, and then we will make two lookups at this particular coordinates. So with the first lookup we will obtain embedding vector for this particular object instance that was detected at this point. In the second lookup we will obtain a variance vector. And then once we have this, we can evaluate probability for every point in this volume of belonging to this particular object instance. And we will assign these points to this particular object instance, and this is how we will get segmentation masks throughout the whole video clip. And then we repeat exactly the same procedure with the second object. So we have exhausted these points that belong to the rider. We take out the next maxima, we look up coordinates, embedding vectors and variances, and based on that we can assign pixels to this second instance. This approach turned out to be very general and versatile, so we applied it to different data sets for video object segmentation, for video instance segmentation, and for multi-object tracking and segmentation. These tasks differed quite a lot, and also kind of videos that we have there differ quite a lot, and on all of them we obtained state-of-the-art results. Okay, so now let's see how this approach can be applied for a task of 4D panoptic LiDAR segmentation. So here in this variant, what we do is we slide a fixed size temporal window over a sequence of LiDAR sensory data. And then from each window we will sample a set of points and will form a 4D point cloud volume. And then we'll pass this 4D point cloud volume through our encoder-decoder based network. On top of the decoder, we will add 4 network heads. So 3 network heads are very similar to those that I introduced in the previous slide. So objectness head is essentially a sort of temporal point-based object detector. Then we have here object embedding and variance heads that we will use to associate points to their respective instances. And we also have here in addition a semantic head that will that classifies each point, classifies into predefined semantic classes. To obtain final results, we can actually obtain final results in an online manner, and we do that by processing overlapping volumes and associating obtained temporal segments based on a simple point overlap criterion. And actually our experiments show that by enlarging the size of the temporal window, we actually quite significantly improve segmentation and especially tracking performance. So let's discuss a bit the results that we get with this method. So first we evaluated our method on existing single scan Panoptix segmentation benchmark, and here we evaluated a special case of our method where the size of the temporal window is 1, so just single scan. And in this setting, our unified single network already quite significantly outperformed existing methods in terms of panoptic quality and mean intersection over union. So these metrics are commonly used for evaluating panoptic segmentation and semantic segmentation. Also worth mentioning here is that several baselines here use separate networks for semantic segmentation, object instant detection, and then fuse results in the post-processing step. And we do everything with a single network. So then we evaluated our method in our proposed benchmark. So we proposed this benchmark in this paper as well, and we interpreted these results based on the novel metric called LiDAR segmentation and tracking quality, which we also introduced in this paper. And this metric, LSTQ, consists of 2 terms. The first one, association term, essentially signals us how well we can associate points in 4D space and time, and essentially tells us how well we can segment and track objects. The classification term evaluates how well we can semantically classify points, and this term takes form of mean intersection over union. So as I already mentioned, in terms of tracking, the most established approach is actually tracking by detection. So here the idea is that we detect and segment objects individually, individual scans, and then we will associate them over time. And here we evaluated 2 variants of this baseline. So in the first one, we use single scan panoptic segmentation methods. We will take instances and then we'll associate them over time using Kalman filter based multi-object tracker. And we here used 3 different methods for obtaining segments on a single scan level. So 2 baselines that are already introduced in the previous slide, and our single scan variant that I also showed already on the previous slide. And these are the results that we get. So of course, as expected, as our method performs better on a single scan level, it will also perform better in terms of association and classification. So in terms of tracking. The second variant of tracking by detection that we evaluate is based on scene flow propagation. So here we use the pre-trained LiDAR scene flow network to propagate segments from one frame to another, and here we observe quite similar trends. But what is here really interesting is that our method that processes several scans in parallel actually performs significantly better from all these methods. So significantly better than our single scan variant that uses tracking by detection approach on top, and it's quite a lot better in terms, especially in terms of association as expected, and in terms of classification. So semantic segmentation is on par with the single scan variants. So overall, the conclusion here is that our single stage unified network quite significantly outperforms tracking by detection baselines, and it actually doesn't need any external methods or networks for the temporal association. And here I have a short video of our system. So here on the left you can see semantic segmentation results, and here on the right you can see instance segmentation and tracking. So on the left, color encodes the semantic class, and here on the right the color encodes the identity preserving instance ID in space and time. Okay, so that was tracking area, point, and pixel, and now let's dive right into the second topic of tracking in the open world. So here I'm very excited I can present our very recent work called Opening Up Open World Tracking, and this is a product of a fantastic collaboration between our research group at Technical University of Munich, group of Bastian Leibe at RWTH Aachen University, and group of Deva Ramanan from Carnegie Mellon University. So first, again, just a note on open world versus closed world recognition. So let's say that we have a large data set such as COCO and labels for a fixed set of object classes, let's say 80 COCO classes. And now if we would train the detector using labels for this closed set, this is what we get. So we will be able to detect persons, we'll be able to detect cars, bicyclists, possibly even traffic lights. But we will be blind to objects that won't quite fit into any of those object classes. So any of those that are not within these 80 COCO classes. And here one big guiding question is, can we actually learn to recognize new classes from raw streams of sensory data that robots actually do observe? And we really think that we can do that, but we need to figure out how to decompose videos into basic units, which I believe are objects. And this is one of the reasons why we are very interested in this problem. So here I was showing video from one of our past work on generic object tracking. So now let me give you some historical perspective on the topic. So even before the term open world was actually cool, roboticists already understood the importance of tracking and segmenting objects without necessarily understanding into which semantic classes they do belong. So the way that they would go around this problem would be they would take LiDAR point clouds, they would cluster them into instances using something like simple spatial proximity based clustering. So this is something that is quite class agnostic. And then they would use these clustered regions to track objects, and often even aim to classify these tracked objects into one of predefined object classes. But the important takeaway here is that with such an approach we can actually track objects even though we didn't recognize them in terms of semantics. Now, in terms of computer vision, me, Jonathan, Luton, and Charles Dave, we all been working on this topic of tracking arbitrary objects. We were actually working on these problems quite independently, looking into different tracking strategies. But one thing that, or two things that all these methods have in common is, so firstly, we were all using category agnostic variant of MASCAR CNN to get input cues for to start object tracks. So it turned out that in vision it's actually quite difficult to get reliable arbitrary object cues based on such a bottom-up grouping as roboticists have been using. And it turned out that Mascar CNN training category agnostic setting can actually quite well generalize to other object classes. Now, the second issue that we were struggling with is how to evaluate our methods. So how to evaluate how well we can actually track objects that were not seen during the training. We could see empirically, of course, that objects that were not present during training were tracked, but there was not really a rigorous way to quantify the performance of unknown classes, and that was a bit frustrating at the time. So therefore, we set with this work to change that and open the first open-world multi-object tracking benchmark. So to put this also into perspective in relation with existing tracking benchmark, if we look at this class distribution, multi-challenge and kitty tracking cover mainly tracking of most frequently observed object classes such as cars and pedestrians, and the recent automotive datasets expand this a bit, cover a broader range of object classes. Now, recently, our collaborators at Carnegie Mellon actually published this wonderful TEO dataset that actually enables us to study multi-object tracking in this long tail, but this dataset or task still focuses on the closed world regime. And actually, in this work, we really take tracking even further wide into the open world. Now, we base our open world tracking benchmark on the Tau dataset, and what we did here was that we first declared 80 classes that are defined in COCO vocabulary as known object classes. So those classes will be seen during the training. An example of these classes you can see here in this word cloud, and visualizations you can see here on the right on top. The remaining classes, and you can see that there are many of them, we declare as unknown. So those will not be seen during the training phase. 300 of these unknown classes will be present in the validation set, and there will be additional 143 classes that will appear only in the test set. So this we refer to this as unknown unknowns. And we really believe that those are actually a reasonable proxy for the wide range of objects that could actually appear out there in the real world. Okay, so we have a data set, we split the classes into known and unknown, and the next question is, of course, how do we quantify the performance? And here we built on our recently proposed higher order tracking accuracy HOTA metric that we published at IJCV last year, and we adapted this metric for open world evaluation. So in this adaptation of this metric that we call the open world tracking accuracy, we have two terms. So the first term here essentially measures recall. So we decided to go for recall-based evaluation because in this open world setting we cannot really define a notion of a false positive. So to do that we would need to label every possible object, which is of course not really possible. So the second term here evaluates the tracking aspect of this task and tells us how well we can associate instances into object tracks. So this term is evaluated with respect to all true positives and takes form of intersection over union over sets of true positive associations, false positive associations, and false negative associations. So those were introduced in the HOTA metric paper, and let me just very quickly explain what these sets are. So to explain this, let's look at the true positive of interest denoted here with red, and here we have with respect to this true positive we have ground true object denoted with dark blue color, and we have here another track, ground true track, denoted with light blue color. And we also have two predicted tracks. So one is marked with the black circles, another one marked with gray circles. So everywhere where these two agree with each other mutually on the identity, so everywhere where dark blue and black mutually agree, we denote those instances through positive associations. In case it happens that another predicted track claims the dark blue track, we obtain false negative association. So this is the first type of errors that we quantify with this association term. In case it happens that black trajectory, the predicted trajectory, jumps on another ground truth object, denoted here in light blue, then we have here the case of false positive associations. Okay, so now we have a test bed, and now let's discuss some some key results. So first of all, in scope of this project, we also devised open world tracking baseline that follows tracking by detection paradigm, tracking by detection design. So input to our baseline comes from mask RCNN that was trained in category agnostic setting. And here, one of the main aims was to rigorously study how to associate object proposals that we get from such mask RCNN over time. And this is how we devised our open world tracking baseline. I won't really have time to discuss all these design decisions here in this talk, but I will outline a few interesting key results. So first, we actually study how well our category agnostic variant of mask RCNN performs on unknown classes, so classes that were not seen during training. Note that here we are not discussing tracking aspect of the task yet. So here on the left you can see detection recall for unknown objects versus number of proposals for different scoring methods. And one of the conclusions here is that it turns out that commonly used two-stage object detectors such as mask RCNN actually generalize quite well to unknown classes. So you can see that we obtain quite reasonable recall, suggesting that they inherently have any object detector built in. We also evaluated different ranking strategies, and as you can see here, we actually can rank our proposals quite reliably. And this is very important because we can't really fit 1,000 proposals to our tracker. Here on the right, you can see track recall at varying percentage of detections that were correctly recalled. So this means that, for example, for 50% detected, it means that at least half of the track must be correctly localized. And here you can really see that there is quite a big difference in tracking known and unknown objects. So for example, only 25% of unknown objects are recalled in every frame compared to 70% for the known objects. And this really shows how data association in open world is actually much more challenging, and this is also why we made a very thorough analysis on how to associate these proposals in the open world setting. So now let's have a look at some key tracking results. So here first let's discuss the results that we get on the validation set, and here we actually compared our baseline, open world tracking baseline, to two closed world benchmark baselines. Those are listed for reference only because those were trained also on unknown classes, so they're not really open world trackers. And what is interesting here is that our baseline performs better than both previous state-of-the-art closed world trackers for known classes. And we think that this is because of a very careful design of our method. So here you can see combined metric, then here we have detection recall, here we have association recall, and here we have association precision, and we are doing better in terms of all three. So of course, as expected, we fall behind for unknown objects because both Oracle methods have been trained to both detect and track these unknown objects, and our baseline was not. And this also nicely highlights the challenges and the gap that we still have for open world tracking. So now moving on to the test set. So this test set actually contains both known objects, unknown objects, and unknown object classes. So these are those that are not even present in the validation set. And what is very nice here, that our baseline actually performs similarly between the validation and test set for known and unknown classes, objects. Even more important, our method performs similarly on the test set for unknown classes, so those that are unique to the test set, as it does for unknown classes that are also present in the validation. Thirdly, we also had a look on how our method performs in closed set conditions. And here we evaluated our method on Davis and Kitty multi-object tracking segmentation. And what is interesting is that even though our method was not tuned for these datasets at all, it's still competitive on both closed world tracking benchmarks. And these were, of course, specifically tuned for these benchmarks. So here on Davis, our method is only lagging behind UNOVAST, as I said, tuned specifically for this dataset. And here on Kitty mods, we are actually on par with state of the art. But of course, I should mention here is that here we are only looking at the methods that all use public benchmarks. Sorry, not benchmarks, public detections. Alright, and now for the end some visual results. So here you can see some tracking results for tracking known objects, and here at the bottom some visual results for tracking unknown objects. And what is particularly interesting actually is that there are also those objects that we track, I don't even know what the name of these classes, that are not even in Tau vocabulary. So these are objects that are not labeled. They would actually be in the closed setting evaluation, it would be considered to be false positives. But here we actually notice that our method tracks and discover these objects, and it's something that we found also to be quite interesting. And now, as a conclusion, I presented here that tracking can be posted as a clustering, and this approach that we proposed is actually a bottom-up approach that can be used for a variety of multi-object tracking and segmentation-related tasks. It's also directly applicable to holistic and dynamic visual scene understanding, and we applied it to both video-based input and LiDAR sequences. And I hope that I motivated you that the next grand challenge that we need to all tackle is open world tracking, or more generally open world perception. Thank you for your attention.